All right, welcome back. Today, let's talk about the method of sections. So, if you don't want to necessarily, you don't want to know the forces in all the members of a truss, but only a select few. You don't have to use the method of joints to go analyze the truss joint by joint. We can use the method of sections. It's a very nice shortcut when you only want to know, as in this problem, the members, the forces in a few members. So this is problem 5-36, and so go ahead and turn to that in your book, and then you can get a clear picture of what's going on. This is kind of small here, but you can read that the problem is to determine the force in members LK, LC, and BC. So there's three members that we're asked to determine forces in. Let's identify them. So BC is this member right here, and LC is the member above it, and LK is this third member. So to use the method of sections, we're actually going to imaginarily cut through those three members and draw a free body diagram of one side of that section or the other. In other words, we'll make a cut right through here, and I'll take this side over here and do a free body diagram of that. But before we do that, let's determine our reaction forces. We'll be needing them. So we have a reaction at G. Stand by, I'll get my blue pen. Here we go. Hello. So we have this is on rollers here. So we have a reaction force at G. Call it GY. And we have a reaction force vertical. This is pin, so it's got two reaction forces. One is vertical and the other is horizontal. So I'll go ahead and draw them in. AY, and give them a name, AX. And I can already see that AX is going to be 0. The reason I can see that is because it's the only horizontal force represented in this truss. So when I summate forces X equals 0, A sub X equals 0. So we don't need to worry about that. But we do need to find, since I've decided to analyze this side over here, I do need to find what our reaction force is. So if I summate moments about G, I can solve for AY. So let's do that. Reaction forces. So summate moments G equal to 0. And I'll just say that this is positive. Oops, you can't see it like that. So let's go ahead and do that. We see that we have AY causes a negative rotation. So we have a negative AY times 1, 2, 3, 4, 5, 6 times 4 is 24 feet. And we have a 3,000 that causes a positive rotation. 3,000 pounds times 1, 2, 3, 4, 5 times 4 is 20 feet. Another 3,000 pounds times 1, 2, 3, 4 times 4 is 16 feet. We have a 4,000 pounds, causes a positive rotation, and it's got a moment arm of 12 feet. And we got a 2,000 pound with a moment arm of 8 feet. And finally another 2,000 pound with a moment arm of 4 feet, equal to 0. So one equation, one unknown. That makes us happy. And when we solve that, we get AY equals to 7,500 pounds. Vertical up. Comes out positive, so we guessed right. And we have that. Reaction force is 7,500 pounds here. So now we can go ahead and draw the free body diagram. Let me adjust this camera here a little bit. Free body diagram of the area that we decided to section. So let's do that. Alrighty then. So I want to, whenever you cut through a joint, then you're going to reveal the forces in the joint. I'll show you what I mean. So here is A, L. So I'll let this represent A here, and I'll go across and draw, let's see, where is it? There it is. Go across and draw the horizontal members. Like that. So this would be A here. And we have this vertical member LB coming down. So let's draw that in. So there's L. Here's B. I'll just put a B right here. Should probably draw that bigger. And then, now see on this B, section BC, we cut it. So we basically cut through there, and we can replace that member with the force that acts through that member. And we don't know if it's compression or tension, so let's just assume that it's in tension and give it a name, force BC. And likewise, we cut through this member LK, and so we need to replace that member. We need to put a force there where that member is, and we don't know if that's tension or compression, so we'll assume it to be tension and give it a name, force LK. Oh, we cut through another member here too. We cut through LC right here. So let's draw that in, LC. And I'm going to just cut this, I'm going to erase this back a little bit. I was a bit aggressive on how long I drew it. Let's just make it a little bit. So that's force BC. Just so that I have room to draw force LC out in this direction somewhere. So there's force LC. So that's a good start for a free body diagram of the section that I've chosen, except that I need to put a vertical force AY happening here, 7,500 pounds. And we know a little bit more about this guy. We're going to need to know some directions, and so we need to define our slopes. Like for force LC, we can figure out what that slope is like. Let's do that. So let's look at from A to B is 4 feet. For A to B is 4 feet. This could be a 3, 4, 5 triangle. It is. As you can see, A to B is 4 feet. The vertical distance is from A to L is 3 feet. So that makes that a 3, 4, 5. I'm sorry, a 3, 4, 5. So what I mean is that this is 4, this is 3, and this is a 5. That's a 3, 4, 5 triangle. And looking at the diagram, it's all so very symmetrical that these two are 3, 4, 5 triangles. So actually we could draw 4, 3, down here, 4, 3, 5. Because that's a 3, that's a 4, and that makes the slope of 5. That's pretty handy to know. Let's see, can we do the same thing? Sure, up here as well. This guy is got a slope of 5, and the vertical distance from L to K is 3, so that also makes this a 3, 4, 5 triangle. This is 5, vertical distance is 3, and the horizontal distance is 4. So that makes analysis easy. All right, so take a break right here.